So this week we want to study primarily resistors and resistance and resistivity. But it's related to conductors, conductance, and conductivity. So we'll make sure that we understand how these two things are related. And we'll also want to relate it to what we just did, capacitor, capacitance. Capacitor is the device. So we have, whoops, I didn't show you last week, but if you watch the Khan Academy videos, capacitors in circuits vary a lot from very tiny little disc-looking things to fatter ones, and then these rolled-up type devices. And the rolled-up type devices are the older models of capacitance, and they're basically two pieces of conducting foil with a dielectric, like a piece of plastic between them, rolled up. So if you cut this open, it would unroll into two long pieces of foil with a conductor between it, because we know that a typical, simple, standard capacitor, we didn't get to do this, but we have these in lab, where we have two plates that are the same area, and we can slide them back and forth and close the gap between them. So a basic idea of a simple capacitor is this, but in practicality, when you see them in circuits, they're going to look like this, and you don't see the plates. So the plates are inside these devices, or in the case of these cylindrical capacitors, they're foil wrapped up. Okay, so just so we launch from what we know, I want you to write down the definition of capacitance and the equation that tells you what capacitance depends on. Write those two equations down and then come back. I hope you recall from last week that the definition of capacitance is the charge per unit volt. And that should be logical to you, right? How much charge the device holds per unit volt is its capacity. So if 1 volt means 10 nanocoulombs, that's a certain capacity. If it's 20 nanocoulombs per volt, it's twice as much capacity. So this makes a lot of sense, but it doesn't, the capacitance is the device itself doesn't depend on the charge and the voltage, because if I double the voltage, the charge will double. This is a constant. What the capacitor depends on is the characteristics of the device. So it depends on the area of the plates, separation of the plates inversely, and the epsilon naught, the electrostatic constant, and the material between the plates. So if we have air, this is 1, but if we put some other material, that will raise it. So 3 factors: the material between the plates, the distance between the plates, and the area between the plates. So this is what we learned last week. And now we want to go to, before we talk about capacitance, I want to talk about conductance. I mean resistance. We'll talk about conductance first. So a conductor, what's the simplest possible conductor? A wire. And so how do we define the ability of something to conduct? Well, in order to talk about that, we have to, first of all, define current. So the ability to conduct is the ability of the wire to have current pass through it. So if it's a good conductor, a lot of current will pass through per unit volt. So similar to this equation, conductivity, we can't use C because we already used it, so we use G for conductivity. G is the ratio of the current we get, rather than the charge, per unit volt. So current, we'll learn later, is the flow of charge, and it's measured in amps. So if we get 1 amp for 1 volt, that's a certain level of conductivity. But if we get 2 amps for 1 volt, that's more conductivity. So this is how we define conductivity. And yet, the conductivity of a wire doesn't depend on the voltage of the current. It depends on the wire, the characteristics of the wire. And so think about what's going to make a wire a better conductor. So that's called its conductance. And for conductance, the symbol used happens to be sigma. That's not important. But what's it going to depend on? Well, the wire, it will depend on the length of the wire. So the length of the wire, is that going to make it conduct more or less? The longer the wire, the less it's going to conduct. And how about the thickness of the wire? Well, what's important about the thickness of the wire is not its diameter or its radius, it's the area of the wire. So if we take a wire that's twice as big, the area becomes 4 times greater. And that means more conductance. So the area of the wire. And in this case, it also depends on what the wire is made out of. And that's what we call the conductivity of the wire. Now I forget what that symbol is. Okay, so 3 things will determine the conductance of the wire. The area, more conductance; longer wire, less conductance; and the material it's made of, the property of the material it's made of. Okay, now when we come to, so that parallels capacitance, the ability to hold charge, the ability to conduct charge. Except in circuits, we use resistance more than conductance, and resistance is the opposite or the inverse. So what's the opposite of its ability to conduct? It's the ability to resist. So these things get inverted. Oops. Let me just get these out of the way. So a resistor, anyway, I got some resistors here. Let me fix this. Okay, I got that fixed. So conductance, as we said, is defined as how much current we get per unit volt. So more current per unit volt means a better conductor. The conductance, here's where I messed up on the symbols. The conductance of any wire, though, depends on the physical characteristics of the wire. And that's the cross-sectional area of the wire, the length of the wire, right? A longer wire, less conductance; more cross-sectional area, more conductance; and the material of the wire. So this symbol is the conductivity, and this symbol is the conductance. Now, since resistance is the inverse, we do use the symbol R for resistance. And so it is 1 over the conductance, the inverse of it. And so this reverses. This is 1 over sigma L over A. So the longer the wire, the more resistance it has. And the bigger the cross-sectional area, inverse to conductance, the less resistance it has. And 1 over the conductance is actually what we call the resistivity. So we don't use 1 over the conductance. We have a number or a quantity for the property of the wire that makes it a better or worse conductor. Like copper is a good conductor. And so the symbol for resistivity is rho, the same symbol we use for density, lowercase rho. And so if something's a good conductor, its resistivity is low. If something's a poor conductor, its resistivity will be high. And so we introduce this because it's important to understand the connection between these two, but this is what we're going to use. And so the resistivity rho is equal to the 1 over the conductivity, sigma. But the thing about resistivity is it does depend not just on the material, but on the temperature. So a wire, when it's heated up, it turns out it has more resistance and less conductivity. And so the other equation that you'll see on your equation sheet is the relationship between resistivity and temperature, and it looks like this. So this alpha is called the temperature coefficient. Temperature coefficient. And so every material will have an intrinsic, say aluminum. It has an intrinsic resistivity, but that varies with temperature. And if we want to know that, we have to know the temperature coefficient. And the rho naught means the rho at room temperature. It doesn't mean the resistivity at 0. It's usually measured from room temperature, which is generally taken to be 20 degrees Celsius. So these are the equations that we're going to use this week to solve the problems in the assignment. And while I have it here, so when you see resistors in circuits, they look like this. You've all seen circuit boards, and these are resistors, and the colored bands tell you how much resistance each resistor is. And yet, we're not talking like capacitors. We're not talking about the actual devices. But here, if we wanted to make a resistor just out of wire, we would have something like this. And we actually have these in lab, where you have a cylinder and you have wire wrapped around it. And depending on the thickness of the wire and the length of the wire and the material, this resistor will have a certain resistance. It also has a slider bar that allows us to adjust the resistance by taking more or less of the wire. And you see a meter in this picture. Okay, I was cleaning up the screen and realized I forgot one important thing. I wrote down that resistance is 1 over the conductance. But if I take this equation, what I get is that this is V over I. So the definition of conductance is this, and the definition of resistance is this, and the equation on which the resistance depends is this. So remember, when we had capacitance, the definition was different from the equation that determined the capacitance. Okay, I'm going to clean this up and then come back. Okay, let's summarize what we learned, and I've written down all the equations that you will see on your equation sheet and the equations you need for this week's assignment. So the resistance of a wire is 1 over the conductance, the inverse quantities. And since conductance is current per unit volt, resistance is the opposite. This in the end will be why resistors in series and parallel are different from capacitors, because we're doing the inverse relationship resistance. So this is our definition of resistance. And this definition of resistance rewritten becomes the relationship between voltage, current, and resistance, and is a widely used relationship called Ohm's law. So this is Ohm's law, and it's what we use all the time when we're doing circuits. All right, but what does a resistance of a wire depend on? It depends on the material, it depends on the length of the wire, and it depends on, don't just say the area, the cross-section area of the wire. And, whoops, there's a mistake here. This should just be rho. And the resistivity, that intrinsic property of the wire to resist the flow of current, is temperature dependent. And so we have the equation that relates the resistivity to temperature. And so usually when you look up resistivity of a material, they'll give you the room temperature resistivity, and they'll tell you the temperature coefficient. And then you can calculate the resistivity of that material at any temperature. And if we multiply this by L over A, we can turn this equation into a useful equation, which will be useful in the assignment, that the resistance at any temperature will be equal to the resistance at room temperature, 20 degrees Celsius, times 1 plus the temperature coefficient times the change in temperature. So there'll be problems where you'll want to use this. It's important, though, at this point to understand what we mean by current. And current is the flow of charge. So when we think of a circuit, and it's important because you'll see later on when we do circuits, you don't want to be confusing voltage and current. Voltage is the energy difference between 2 points. So you always measure the voltage across something, whereas you measure the current through something. And so current is like the flow of traffic. You would count how many cars go by a point. You count how many charges go by a point per second, and that's the current. Well, this would be the average current. If the current is varying, then you would take the derivative of charge with respect to time, just like the concept of velocity, right? The derivative of distance with respect to time. So this is our definition of current. That's the concept. And the last thing is power. So usually we don't talk about energy in circuits because they're dynamic, because they're always using energy. So we talk about how much energy they use per unit time. And so you'll remember that energy per unit time is joules per second. And a joule per second is a watt. Remember that from last semester. And if you don't remember, that's what it is, joules per second and watts. Watt is 1 joule per second. So when we define power, you look at the energy, the electrical energy per unit time. And the energy, remember, is always the charge times the voltage. That's how we found the energy on a capacitor. And so if we take the energy and divide it by time, we have Q over T, which is current. So the basic power equation is current times voltage. But if we use Ohm's law, and we want to substitute out the current as being V over R, then we would get that the power is V squared over R, or I squared R, simply by substituting out. So these aren't 3 different equations. They're just variations of the same equation using Ohm's law. So this, you'll find all this on your equation sheet. This is the equations you need to do this week's assignment. You're ready to go.